Okay, welcome back everybody. This video is the 10th video in the series and it's integration for inverse trigonometric functions. Within this section, I need to also teach you or remind you how we complete the square. So many times I'll ask you to pause the video and write down some steps because it's extremely important that you know how we complete the square specifically for these type of integrations. So let's get started with the integration rules for inverse trigonometric functions. What I want you to know is that there's three major rules that we'll be using. There's the arcsine, arcsecant, and arctan. Now, remember that whenever it comes to integration, whenever it comes to finding the antiderivative, it's always about finding a particular pattern. So if any one of our functions fit one of these patterns, then we can easily find the antiderivative. Now, of course, there's always some modification that's required, and we'll do a couple of examples throughout this video so I can show you how we modify and change if we need to change. So let's get started with the first example. I have the integral of 1 over 4 plus x minus 3 all squared. Fantastic. I try to find which pattern it fits, and if we look carefully, it looks like the third rule, whereby we have a squared plus u squared. Okay, so what is the value of a? 2. What is the value of u? X minus 3. So pretty much it's simply a plug and play. We just write in the values, and there's my antiderivative, and don't forget to add plus c, my constant. Okay, so let's take a look at some more challenging examples, ones in where something may be missing and they need to modify, or just simply rewrite the question or rewrite the function in a different form so that it fits one of those patterns that we saw before. So let's take a look at the second example. We have 3 over 2 times the square root of x times 1 plus x dx. Okay, so the first thing I'm going to do is I'm simply going to rewrite this. Now 3 is a constant, so I can take out the constant, and I have 1 over 2 times the square root of x times 1 plus x dx. Okay, it still doesn't look like any one of the patterns that we saw earlier. It doesn't look like any one of the inverse trigonometric functions yet. So this is what I'm going to do, and you're going to understand why soon enough. I'm going to let u equal to the square root of x. And if I take the derivative, du dx is equal to 1 over 2 times the square root of x, and cross multiply, I get du is equal to 1 over 2 times the square root of x dx. Okay, well I do have 1 over 2 times the square root of x dx. So therefore, it starts to kind of resemble, or it actually fits the pattern of the du part. So what I'm going to do now is this. I'm going to rewrite this again, and this time I'm going to write it with the square root of x squared, because what we have to remember is that the square root of x all squared is equal to x. So all I'm doing is I'm rewriting it in a different form that will actually fit the pattern. So now we have our function, we have our u prime, which is 1 over 2 times the square root of x dx. So all I simply need to do is simply rewrite everything, but in terms of u. So now I have 3 times the integral of 1 over 1 plus u squared du. Remember what du is. Du is 1 over 2 times the square root of x dx. Fantastic. Does it fit one of the patterns? And yes, it does. It fits the arctan pattern. So it's du over a squared plus u squared. A is 1. U is the square root of x. So therefore, I simply write down my information, and there's my antiderivative. This one was a little bit more challenging because we needed to rewrite and we needed to remember or think of that little trick whereby x is also the square root of x squared. Now, what's important is that we need to know how to complete the square for this section. Now, it's been probably a long time you haven't completed the square, but when it comes to the integration of inverse trigonometric functions, it's extremely important that we know the technique of completing the square. So let me show you once again, let me refresh your memory on how we complete the square. So let's start by reviewing some of the important steps for completing the square. Now what I want you to do is I want you to pause the video and I want you to write down these 6 steps, and I'll explain each step to you. So the first thing we need to do is we have to rewrite the quadratic in decreasing power. Now remember, most of the time it's already given to us, most of the time it's already written in decreasing, but in case we need to, we just modify, write them in decreasing power. However, it is extremely important that completing the square only works with quadratic. And what's the reason for that? Because we're trying to change the look of the function. We're trying to change the look of the quadratic. we're going from general form to standard form. And in doing so, it ends up resembling one of the integrals of the inverse trigonometric functions. So, next thing, what we need to do is we need to group our x's together. So we're going to put brackets around our x's and we're going to leave the number, the constant, on the outside. Step 3, if it so happens that there's a leading coefficient of x squared, so in this case 2, we first have to factor out that value before we do anything else. And I'll do an example with you a little bit later on in the video. The most important part, how we complete the square. We need to take half the value of the leading coefficient of the linear term and square it. So in this particular example, 6 is my leading coefficient. So if I were to take half of 6 is 3, and then I would square it 9. So then what I would do, I would simply add 9 and subtract 9. Now remember that we can add 0 to any expression. But instead of writing 0, we're changing 0 to positive 9, negative 9. And the reason why we're doing this is because we're trying to be able to complete the square. We're trying to change the look of this function so that there's a perfect square in it. And it just so happens that x squared plus 6x plus 9 actually is a perfect square. So we have x plus 3 squared minus 4. And now this actually fits one of the patterns for the integration of inverse trigonometric functions. So I'm going to go ahead and give a couple of examples on how we complete the square and how we find the antiderivative of these trigonometric functions. Let's take a look at some examples for completing the square before we continue into the actual integrating part of it. So we have x squared plus 6x minus 5. Fantastic. There's no coefficient in front of the x squared, so all I simply have to do is put brackets around my x's. Okay. Now remember that to be able to complete the square, I need to add something and subtract something. So, how do I find what I need to add or subtract? I simply take half of the linear term, in this case 6 divided by 2 is 3, and square it. So I'm going to add 9, and I need to subtract 9. Remember that any expression can have, 0, but I'm changing 0 to be plus 9 and minus 9. Now what happens here is that I just created a perfect square. So x squared plus 6x plus 9 simply becomes x plus 3 all squared minus 14. Okay, fairly simple. The next one, a little bit more challenging because now we have a coefficient in front of x squared. So, same idea, I'm going to put brackets around the x's. However, now I need to factor a value out. I need to factor 2 out. So it becomes x squared plus 2x plus something minus something. Now try to get into the habit of writing it down like this form. If you write it in this form, it's going to be a lot easier to fill in what's missing, what you're adding and what you're subtracting, and therefore much easier to transform it from general form to standard form. However, this one's a little bit different. Remember that we're trying to add 0 to every equation. So the first bracket, what I'm going to do is I'm simply going to take half of 2. Half of 2 is 1, square 1, and I get 1. However, what I'm going to do is I'm going to actually subtract 2. Now, where does this 2 come from? Well, remember that we have a coefficient. So, I have 2 times 1, which is 2, and then I need to subtract 2 to get my 0. So, don't forget that whenever there's a coefficient, you're going to multiply that coefficient by the number you just added in so that in the end, they cancel out and become 0. And then finally, of course, we have 2 times x plus 2 all squared minus 5. And there we go. That's how we complete the square. So integration with completing the square. You're going to notice that these examples get a little bit more challenging as we go. So the first example, we have dx over x squared plus 4x plus 9. It doesn't fit any of the previous patterns that we've done. So what I'm going to simply do is I'm going to rewrite this. So since there's no leading coefficient, it's simply x squared plus 4 plus something plus 9 minus something. What is that plus something? Well, half of 4 is 2, 2 squared is 4. So I'm going to add 4 and I'm going to subtract 4. Finally, I'm simply going to rewrite this in the proper form, which is x plus 2 all squared plus 5. Fantastic. So this resembles u squared plus a squared or a squared plus u squared. Okay, we can just simply rewrite it. And of course, we have dx over x squared plus 4x plus 9 is equal to dx over the square root of 5 squared. Now remember, the square root of 5 squared is simply 5. That's why I'm rewriting it in this form, so that this way you can see that a is the square root of 5. So, simply use the formula that we saw before, which is du over a squared plus u squared, and of course 1 over root 5 arctan x plus 2 over root 5 plus c. And we're done. There's my antiderivative. Okay, the second one is a lot more challenging. Now, sometimes you're going to have to modify the look of a function so that it satisfies or it helps fit one of the specific examples or one of the integration rules that we have. So you probably wouldn't have thought of this on your own. That's why I showed you the specific example. But remember that many times what I'm showing you now will show up quite often as you keep on doing problems. So what we're going to do is we're going to simply rewrite this. Now, if I take a look at this thing, the first thing that comes to mind is ln u prime over u. Now, u prime would be 2x plus 2, but I have 2x minus 5. So, is there a way that we can simply rewrite negative 5? And there is. I can simply rewrite negative 5 as 2 minus 7. Why am I doing this? Because I need to realize that this can be rewritten with two integrals. So the first one becomes 2x plus 2 over x squared plus 2x plus 2, and the other one becomes 7 over x squared plus 2x plus 2. Okay, now the first integral, if you look carefully, as I said previously, u prime is 2x plus 2. So therefore that has to do with the logarithmic integration. And we saw that in the last two videos. So I know that now we have x squared plus 2x plus 2. Here I'm going to need to complete the square. So when I finally complete the square, I end up with 1 plus x plus 1 all squared. The first integral is logarithmic. The second one is inverse trigonometric. Final answer, the ln of the absolute value of x squared plus 2x plus 2 minus 7 times the arctan of x plus 1, and then of course plus c, my constant. So as you can see, sometimes you need to rewrite, modify the question so that it will fit one of those forms that we're looking for. So let's take a look at some practice examples. So we're going to take a look at the first one, which is an indefinite integral. And then, of course, I'll show you an example of how do we evaluate a definite integral. So the first thing I'm going to do is I'm going to break this up into two separate integrals. And there's a reason why I'm doing this is because if I take a look at the 1 minus x squared, and if I were to take the derivative of that, I would end up with negative 2x. And I have a 4x. So something seems to be missing. I need to modify a little bit for the first one. And if I look at the second integral, it seems to fit one of the patterns that we have, which is the sine inverse or arc sine. So let's get started with the first one. We'll let u equal to 1 minus x squared. We're going to take the derivative, du over dx equal to negative 2x. We're going to cross multiply. And we're going to solve for x dx. Okay, remember that 4 is a constant which can be factored out. And of course also the 3 is a constant which could be factored out. So I'm just simply going to rewrite this. I can multiply 4 times negative a half. And I have negative 4 over 2 times the integral of 1 over the square root of u du plus 3 times the integral of 1 over the square root of 1 minus x squared. Okay, simplify it a little bit further. Negative 4 divided by 2 is negative 2. And this is what we have. So the first integral requires just regular anti-differentiation. We bring it u to the negative a half. We add 1, divide by n minus 1, n plus 1, sorry, and we should be okay. For the second one, we have to notice that it fits this particular pattern, which is the arc sine. So the first one is simply u to the 1/2 over 1/2, and the second one we have a is 1 and u is x. Replace and simplify, and there is my antiderivative. Okay, the second example is a little bit different because we're going to evaluate this definite integral. We should notice that it fits this specific pattern, which is tan inverse. So we have 1 over 9 plus x squared. A would be 3, u would be x. I simply replace and now evaluate f of b minus f of a. When I do this, be very careful, because when I need to enter this into the calculator, arctan is really tan inverse. So remember that, 1/3 tan inverse 1 minus 1/3 tan inverse root 3 over 3. And when we finally evaluate this, and we did this properly, we end up with a value of pi over 36. So I gave you an example of how we find the definite integral, and I gave you an example of how we find the indefinite integral, using, of course, the inverse trigonometric functions. Last and not least, practice, practice, practice. Like I say in every video, the more you practice, the better you'll get at these different techniques. Now remember, if you've been watching the last few videos, it's all about identifying a specific pattern, and once you've identified that pattern, then you use the rules for anti-differentiation. Now, we've also seen that sometimes some modifications are required. Don't forget that it's specifically for the inverse trigonometric functions that we have to complete the square. All right, hope you enjoyed.